Good evening, everybody. My name is Helena Rubinstein-Dunlop. I come from School of Mathematics and Physics at the University of Queensland, and it gives me great pleasure to be able to introduce to you today's speaker, Professor Andrew White. Before I do it, I would like to tell you a little bit about the International Year of Light. So this lecture is given under the umbrella of International Year of Light. So what is it? United Nations has announced 2015 as an International Year of Light to celebrate light and light-based technologies, to make sure that we understand the revolutionary role that light has played in our society, both in industry and in our everyday life, light too, slip of a tongue. And so we are trying this year to make sure that everybody around us understands and appreciates the importance of light in our lives and industry, and understands where it is leading and what sort of fabulous developments have taken place which are able to give us the world that we are living in. So this is in medicine, this is in communications, internet, wherever you look, there will be light around you, which made it all possible. But I will let Andrew talk about it. Before we do that, I would like to screen a little film for you.
Our days begin with light. Light, you see, is everywhere. Light is life. Light connects us with others, near and far. It entertains and inspires both young and old. Light enables us to see things never imagined. It will drive economies of the future. With light, we can diagnose and treat disease. It helps protect and secure our communities. Light will be key in discovering solutions to society's most pressing problems. And as the lights go down around the world and our days end, our future will continue to be enabled by light.
So we're celebrating light today. The talk of today is under the umbrella of another fabulous events that have been going on for many years, and many of you know those events very well, and this is BrisScience, and I will let Joel Gilmore introduce this part. But just a few words about today's speaker. So today's speaker is a Queenslander through and through, Professor Andrew White, who will be talking to us about light fantastic. And light has formed a big part of Andrew's life from early on. Andrew is a graduate of University of Queensland, and then he decided to see wider world and went and did his PhD at ANU, with a stint in Germany and then in the United States. But then he couldn't live without Queensland, so he came back. And so he's here. He's a very proud Queenslander who is trying to tell us everything there is about light fantastic. His science has a lot to do with light, if not everything, and we'll hear more about it. But before we do that, Joe.
Thank you very much, Linda. So good evening, everybody, and welcome to BrisScience. If this is your first time along, fantastic. Thank you so much for coming. It's great to see all the UQ alumni people here for this shared event tonight as well. So BrisScience is a series of free public lectures on science held about once a month, where we bring not just the best researchers, but also the best communicators, and in Andrew's case, entertainers as well. So we're really excited to have everybody here tonight, and Helena has also been a long-time supporter of BrisScience, so thank you very much for your ongoing commitment to making this happen. Just a few little bits of housekeeping before we bring Andrew to the stage. First of all, if you have a phone, now would be a great time to turn it to silent. And also, if you have a phone with Twitter on it, then you can tweet throughout the talk, and there will be other people tweeting up the back as well. And it's a good moment to introduce how we do questions at BrisScience. Now, Andrew has said he is happy to take some questions throughout. So if you have a burning question, feel free to throw up your hand or throw something at Andrew, or whatever it takes to get his attention. But at the end of the talk, we'll also be taking questions through the question slips that you have on your seats. So as the talk goes on, write down any questions you might have, and at the end, Leonie and others will come around and collect those questions from you, and we will pick out as many as we have time for, and then we will have some chance to chat to Andrew afterwards. Also, of course, we'll take questions on Twitter, #BrisScience. I don't think there's any other housekeeping for just now. We'll talk about next month's talk at the end. So without further ado, could you please welcome to the stage Professor Andrew White.
Thank you, Joel. Thank you, Helena. That was a particularly gracious introduction by Helena, and I should explain why I'm very touched, because I was one of her first students, and I think she's finally forgiven a friend and I who nearly set her on fire in a sodium explosion in 1990. So thank you, Helena. Joel has less to forgive. He just had me as a lecturer. So today's thing is the Light Fantastic. As you've heard, we're at the University of Queensland. A lot of the research that you'll be hearing about has been sponsored by the Australian government through the Centres of Excellence, one in Engineered Quantum Systems and one in Quantum Computation and Communication Technology. Let me just go back to the Year of Light logo, because I only just realised today that these are flags. So to represent this is the International Year of Light, this is all different flags around the world, and I just thought it was some wavy thing, so I hadn't really paid attention. So light really is, understanding it has been an international endeavour for a long time. So one of the earliest people, and apologies for my awful Greek, Empedocles, 2,500 years ago, believed that Aphrodite made the human eye out of earth, wind, water and fire, and then lit the fire in the eye, which shone out from the eye. And that's where vision worked. Okay, except you should be able to see at night. Said Empedocles, but there's an interaction between the eye and the sun, and that's why you can see during the day. And that was good theory for 500 years, until Lucretius came along in his famous work on the nature of things in 55 BC, and he more or less nailed it. This is 2,000 years ago. The light and heat of the sun, these are composed of minute atoms which, when they're shoved off, lose no time in shooting right across the interspace of air in the direction imparted by the shove. That's quite an extraordinary translation. Sorry about that, I'm not a Latin scholar. But then I think most impressive of all was this fellow here, Hassan ibn al-Haytham, who lived at the turn of the last millennia, and who did an awful lot of work on light, including a lot of experiments that were then repeated 600, 700, 800 years later in Europe, some of them in ignorance of his work. He argued that sight is due only to light entering the eye from an outside source, and there's no beam from the eye itself. That had really stayed in Western understanding for a long time. This, by the way, is the 10,000 dinar note from Iraq. He gave a number of arguments to support this claim, the most persuasive being the camera obscura, or pinhole camera. Now, they had been around for 1,000 years, which is an amazing thing. If you're ever in Scotland, there's a full-sized room, one set up the Royal Mile. You can go, and it's very impressive. You get this view of Edinburgh. But it's been appreciated for a long time. So that people had an understanding that light travelled in straight lines. And then Newton came along in 1600s, and he worked on mechanics. And he said, look, I know about things that travel in straight lines. They're particles. So I think light is a particle because it travels in a straight line. And he did famously experiments in his optics work. And so that became accepted canon until 1800. And then in 1800, a most extraordinary thing happened. A polymath, a guy called Thomas Young, who worked on decrypting Egyptian hieroglyphs, amongst other things, came along and did a very simple experiment and said, look, light is a wave because I can get interference fringes. Okay, so let's just talk about the difference between waves and particles for a second. If I have a pond and I throw a rock into it, I get lovely ripples coming out from them. They're the waves. And if I'm looking right down on top of the pond, I can get shadows in the water that look like that. If there's a wall across the pond with a little gap in it, you can see this sometimes in piers and jetties, you can see a new source of waves coming out. And we call that a pinhole. And if I have two sources of interference. I dropped 2 rocks at the same time. I made the mistake of telling my kids this once, and we ended up dropping a lot of rocks into a nearby pool, which we had to clear all out. But you can get a whole lot of ripples on the water, and you'll notice something weird. You get this fan-shaped effect on the ripples. And where the ripples are super choppy, that's where the 2 waves are both oscillating in phase together, and you get what we call constructive interference. Where the ripples are calm and the water is almost flat, and if you put a little bit of styrofoam or something on there, it hardly moves at all, there the 2 waves are 180 degrees out of phase, so when this one's going up, this one's going down, and when they add, the water just stays calm. And we call that destructive interference. So that's waves. We're used to seeing waves, particularly coming from the coast here in Australia. What about particles? Well, particles is things, stuff, atoms, planets, frogs, anything you can count. You know where things are, you know where they go, although I made the mistake of showing this slide to a British friend of mine earlier in the year. So it seemed obvious to a long time, light went in a straight line, it was a particle. So what was Young's experiment? Young literally took a nice sunny room, in England mind you, so it must have been the one day of the year, but he put a hole in the wall and he shone the sunlight onto another piece of card that had 2 holes on it, and he looked at the card behind the screen. And with one slit open and the other one blocked, he observed a band of light. Well, that's what you would expect. And with the other slit open and that one blocked, he observed a different band of light. And with both slits open, well, what would you expect? Well, if light is like little cricket balls that you're throwing through, you'd expect 2 piles of cricket balls kind of behind the fence, so to speak. So you might get 2 kind of dips there or just a big pile. But if light is a wave, you expect something really unusual. You expect darkness immediately behind the slits and a bright thing in the middle where there is no direct throwing of the straight lines. And when he did the experiment, that's what he saw. So now what I'm going to get you to do, hands up if you've got skinny fingers. All right, skinny-fingered people, you do this. Hands up if you've got fat fingers. Fat-fingered people, you do this. Hold it up to light, and if you haven't had too much coffee, nice bright light, hold them very close together, and if you can hold them very still, you can see little fringes of light. And you're repeating Thomas Young's experiment from 1800 for no dollars. This works better on a sunny day. It might work too well in here, but try it. My hands do this, so that's no good at all. All right. So that was Young in 1800, and that was extraordinary because for the first time in 130 years, Newton was wrong about something. Okay? And he was really wrong. The technological discovery of the 19th century was electricity and magnetism and how they related to one another. Magnetism had been known for a long time, static electricity since the Greeks, but alternating electric currents, that was the technological marvel of the 19th century, and Maxwell showed that in fact there's a deep and intimate connection between alternating electric and magnetic fields. That's what light is. And when that came out, that solved it. Light was certainly a wave. And a lot of technology moved on from that. These are a bunch of different coloured lasers here, all of them illegal to bring into Queensland now. The first laser was built in 1960 by Ted Mayman at Hughes Labs in the US, based on some theory by Charlie Townsend and Art Schawlow. And they noticed very early on, let's see if we can see this here. Can people see that spot there? Does it look like basically a nice round spot? Grunt if it is. All right. God, you're worse than my undergraduates. All right, wake up. But they noticed early on when they were building the lasers, sometimes they would get a dark line across this spot. So instead of getting a nice round spot like that, they'd get a dark line across it. And they noticed some regularities. Sometimes they would get 2 dark lines across it in certain patterns, or 3 dark lines, and so on. These lines have rectangular symmetry. Sometimes they would see lines that had cylindrical symmetry, so sometimes you get a dark circle instead of a dark line. And these beautiful flower patterns, which I still like seeing to this day. And that was in the 1960s. That was discovered very early on. And then in the late 1980s, people started seeing some other rather odd patterns, which had just these dark spots, or rings and dark spots. What's going on? Well, it's further proof that light is a wave. What's happening is this half of the wave of the light spot is, say, at 0 degrees in blue. This half of the wave is, say, at 180 degrees in red, and where the 2 things meet, you get destructive interference and there's no light. And so you get that dark line. And that happens even as the wave propagates through space. So the wave fronts are kind of out of step with one another continuously. These colours are kind of hard to look at. These spots are interesting, these dots here. You get this continuous going from blue through to red. And so the wavefront there is a spiral through space, and that's called an optical vortex mode. Yeah, you can get whirlpools of light. It's really rather cool. And in fact, the first people to make these regularly with the cheap, reliable technology was here at the University of Queensland in the early 90s. That technique now used everywhere in the world. This is hard to look at, so what people tend to do is zoom them together, and you can just look at their phase on the patterns there, and just take a moment. That's really pretty. But it also carries a lot of information. Okay, this is out of phase with that. This has a ring. This has, you go blue twice, so that's 2 spirals in space, and so on. Now, these optical vortices or whirlpools are actually useful. So this is, say, 2 spirals, and this is, say, 1 spiral, and it doesn't matter what you do, the intensity pattern that you see is just a ring. Okay, so it doesn't look very interesting, but you can do amazing things with it. So what follows is a movie from Helena's lab where they take these rings of light and they do something with it. So you have to understand, light can be used to cut things. We know that. It's used in eye surgery. It can be used to trap things, like a tractor beam, a la Star Trek. And it can be used, well, let's have a look at the movie. I've always thought this needed a soundtrack, so I added one, Helena. So what you can't see is there's a laser beam around here, and it's attracting these particles in solution and then spinning them up. And you can move them around, you can make different patterns. These are little, I think, polystyrene beads that are a few microns across, just in a water solution. So this is a very old video. They're doing a lot more complicated things now. It's rather beautiful. Nothing dramatic's going to happen. Okay, we'll stop it there. So what that has now given us with light is a toolkit. And the goal is, we hope in a few years, to have the following ability. Take a cell, trap it with a light beam, cut a hole in it with another light beam, reach inside with a third light beam, and turn something around. All non-mechanical, all done using light. So light is certainly a wave, and that only works because of its wave-like properties. So yep, Young, Maxwell, great. Newton, no good. Until 1905, 110 years ago, this young patent clerk from Switzerland, and that was about his age at the time, there's his baby son, Albert Einstein or something, came along and said, hey, there's a whole bunch of recent phenomena the last 10, 15 years that we can't explain if light is a wave, but if light is a particle, all of these things, black body radiation, photoluminescence, photoelectric effect, ionization of gases by ultraviolet light, I can explain them all if light is a particle. Now, that's on the basis of then 105 years of successfully thinking about light as a wave. So who is correct? Okay, let's take a quick vote around the room. Who's going to vote with Newton and Einstein? Come on, it's a safe bet. You're not going to lose your money. Who's going to vote with Young and Maxwell? Also a safe bet. Well, how do you solve this? Well, this is one way. Light is a particle, it's a wave. It's a particle wave, particle wave. This is my kids, by the way. Checkers, let's sort this petty bickering and resolve our debate like professional scientists. Okay, Sasha, particle wave, and then they get into it. That's normally not the case unless it's been a very long day. Fortunately, physics and science is not a democracy. You just handle things by experiment. So this brings me to one of my very favourite experiments that has been done with light to solve exactly this problem. And it was done by an Englishman named G.I. Taylor in 1909. Why am I thinking there's an Australian connection? Something's niggling it back. I'll come back to me. Who set up an electric light... Pardon? That's... Okay, thank you. Someone in the audience has just pointed out that the bachelor student who worked with him was an Australian. I knew there was an Australian connection. He set up an electric light source, very dim. Even feeble light sources can cause interference. For instance, so a candle burning at a distance slightly exceeding a mile. For the younger people in the audience, a mile is 1.6 kilometres. So if you're looking at a single candle, 1.6 kilometres, 1.609 kilometres away, it's very dim. Okay? And he set up 2 of them in 2 boxes. And in those boxes, he put a piece of cardboard that had slits in it and a piece of photographic film. Again, for the younger people, photographic film. Okay. That's a joke now. 5 years from now, it won't be. Okay. And in one box, he blocked one of the two slits, and in the other box, he left them open. And it was such a dim light source that you could basically leave the photograph in there, the film, for a day or two, take it out and expose it and show that you only had 1 or 2 spots in the film. So there was hardly any light in the box. So he put in 2 new films, left it going for a month, and went sailing in the Mediterranean. This is how you do physics. When he came back, tanned, rested, not that I'm jealous, he found the following. That in the box that had 1 slit shut, he saw a single stripe of light, and in that box, light acted like a particle. And in the box that had both stripes open, he saw bands of light, including a bright band in the middle and dark patches there, and light was acting like a wave. So it was essentially the same experiment with only one difference, 1 slit was shut or not. So light could behave like a particle or a wave. Now, we don't have a month nor a budget to take you all sailing, but what we do have is some modern technology. So let's repeat that experiment. Can we turn on the photon counter, please? Okay, that hum there. So here's a laser pointer, and I've got a little screw-on bit here that will give me an interference pattern. Let me just check it here so I don't blind anybody. We had a bad experience a few years ago. Okay, so we can see, I don't know if everyone can see that, but I can see a bunch of spots there, and then as I tune it open, I'm basically changing a slit in front of it, and I'm getting fringes. And I have here, Joel, shut your eyes, or move, a photon counter, and this, let's just first put it on. What you're hearing here is single photons falling on a photomultiplier. So that's the film, but sped up. In fact, the photomultiplier is so sensitive that smoke would be coming out, but I have in front of it a very thick black piece of glass. This is producing trillions of photons a second. You can hear only a few thousand hitting. Okay, so now that's if I'm doing that, but now I'm going to open it up, form those patterns, and let's see if we can hear the fringes. Okay, then we'll go quiet, noisy, quiet, noisy. And very boring, but that. Here we go. Noisy, quiet, noisy. And you can hear those waves coming, and that's just counting the fringes of light. So that's Taylor's experiment done in 5 minutes. No need to go sailing. Okay, if anyone wants to play with that later, feel free. You can point it at things and count photons, and it's rather fun. Okay. So Einstein pointing that out about light and Taylor doing that first experiment was the start of something called quantum mechanics. And quantum mechanics is the mechanics of very small things. And there's 2 weird things, really there's only 2 weird things about quantum mechanics. One, as Richard Feynman pointed out, is this wave-particle duality. And he called it in his Feynman Lectures of Physics from the 1960s, a phenomena which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. I'm not sure about that last sentence, but it certainly is at the heart of quantum mechanics. By impossible to explain in any classical way, he means if you take frogs and throw them at slits, they'll either go through one slit or the other. No, don't take frogs and throw them at slits, but you don't get wave-like behaviour with frogs. The other one is something called entanglement, and this was something discovered by Erwin Schrödinger in 1935. Oops. Yeah, as you can see from this point here, or this point here, and my students complain I'm unclear. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So let's look at wave-particle duality. We've just talked about a little bit, but let's really play with it. So I'm going to have a light beam coming onto a half-silvered mirror. This is like your bathroom mirror, except it's got half the thickness of silver, so that you half see yourself and you half see the room behind. Now I'm going to shine a laser, like this one, onto it, and I have 2 of these counters, like these things here, sitting afterwards, except they're rather more attractive than this one. And I just send light through, and I get a click. That's one of those clicks I heard before. Or after a while, I send light through, and I get a click up there. And I do that thousands of times, and I count how often I get clicks, and I find half the time I get clicks there, half the time I get clicks there. And light is acting like a particle. That's like standing at the edge of a fence and throwing cricket balls at the edge of the fence. Half the time they'll bounce back to me, half the time they'll go past the edge of the fence. Well, what happens if I extend the experiment, put a perfect mirror there and another half silvered mirror, which is again 50-50? Well, 50% of the light will go there, 50% will come here, and I count clicks, and I see that, again, 25% of the clicks go there, 25% go there, 50% go there. Light's still acting like a particle. It's nothing surprising. But what happens now if I take that block away and put another mirror in? When that was blocked, I got half-half. If this was blocked, I get half-half. So it's a reasonable expectation. Well, let's see what would happen. So I send the light in, you do the experiment, and the light goes there just like before. And you do it, the light goes there like before. Do it again, the light goes there. Hang on. And you find that you can run it for thousands of times, and 0 or very few will go there, and 100% go there. Now, how is that possible if light is a particle? It's not. But if light is a wave, then it could do that. So if I have a wave come in and a wave bounces off a mirror, think about attaching a rope to a fence and wiggling it like this. The thing that bounces back off the fence flips around. So then what happens is the reflected wave is upside down compared to the first wave. This one goes through. It also gets reflected. It's upside down. They add up together, so all the light goes that way. This one that comes through and this one, they're in opposite phase. They cancel. And so now the light's acting like a wave, even though I'm counting single clicks at a time. All right, well, maybe that's because we waited till the end. Let's get clever. And people have actually done this experiment. They send in a little pulse of light. They know really in time where it is. And they wait till it's past that first mirror. So if it's a particle, surely it's either definitely gone that way or it's definitely gone this way. So it can't interfere with itself. And then once it's gone past, it's definitely there, you very quickly shove in a block, or don't. And if you shove in a block when you do the experiment, yep, 25%, light's acting like a particle. But if you wait till it's there, and then you remove the block before the light gets to it, but it's certainly taken this path or it's certainly taken that path, it's still 100% there. And that confused people for a long time, because if the particle is, say, definitely here, how does it know that block's been removed? It's moving at the speed of light. No information can travel faster than the speed of light. What's going on? And that's why we think this wave-particle duality is weird, because it's plumbed into the universe and it seems to break the rules, except it doesn't. Now, light, you held up your fingers before and you didn't really feel the light, and it's not so surprising maybe that light does that. But it turns out everything can act as a particle or a wave. It depends on the experiment. People have done this with electrons, neutrons, atoms, molecules. Okay, they're small. They've done them with buckyballs, which is 60 molecules. They've now done them with long, floppy molecules floating around, flopping around, flying through space that are hundreds of atoms or thousands of atoms, and they see this behaviour. And there is a group in Vienna, led by Marcus Arndt, who are trying to do it with viruses, which would be cool. So there are two ways of looking at wave-particle duality, and let's go back to a 90-year-old cartoon, or 80-year-old cartoon by Charles Addams, of the Addams Family fame. Very famous cartoon. If you're the skier on the right, you think it's weird. But if you skier on the left, you think it's useful. And that's where we are with wave-particle duality today. We had 100 years of, man, this is weird. And for the last 15, 20 years, we're thinking, no, this is useful. We can start exploiting this to do things, to make better sensors, to make better measuring devices, to make better computers or communication systems than we could otherwise make. There's another part to that story, and I'll get to it in a minute. How am I going for time? Okay, I'm going to take a step back. When I was a teenager, there was a computer I really wanted, and it wasn't an Apple II, although I would have killed for one of those, but what I really wanted was one of these Cray XMPs. I was an ambitious child. There was maybe one or two of these in all of Australia. They needed their own half a building, they needed liquid nitrogen cooling and a dedicated staff of technicians, and It made university administrators grumpy, but they were really cool computers. They could do really cool things. The quantum systems in there were the circuits, the diode circuits, and they were basically exploiting wave-particle duality. But 26 years ago, they were relatively rare systems. Engineered quantum systems like that were rare, expensive, and large. But in the last quarter of a century, they've become small, ubiquitous, and cheap. And the way I'm going to try and convince you of that is, here is, from Gumtree, an iPhone from 4 years ago. Ugh, who wants a 4-year-old phone? Can't give it away. In fact, you can buy them for about $50, $100. If you do, and you pull it apart, and you should do that, it's really fun. Even if you can't put it back together, it's really fun. You get all of this. You get bits. And the bits are control systems and sensors. And when I say sensors, I'm talking about an RF antenna, global positioning sensor, magnetic field sensor, capacitive touch sensor, accelerometer, gyroscope. It knows where it is in space in absolute orientation. Noise cancelling mic. It's got optical sensors, high def, low definition, these days infrared and low light sensors. Okay. Oh, and by the way, it's got a computer far more powerful than the Cray from a quarter of a century ago. And it's now a throwaway item. And if you pull apart the bits, take this chip, it's about $20. It's the gyroscope inside the iPhone. And there's a company called Chipworks who, for fun, pull these apart when they come onto the market. So you're zooming in now with an electron microscope. You're getting smaller and smaller onto that chip. You can see the mechanical detail. This is the smallest mechanical element on that gyroscope chip. Those vertical veins there are 3 red blood cells wide. It's a $20 throwaway item from a 4-year-old phone. Now, that's today. Well, that's 4 years ago. Where are we going to be in 16 years? In 16 years, all of that is going to fit inside a red blood cell. Okay? But when we get to that, now we're so small, we have to start worrying about quantum effects. And we're going to have to not only build all the sensors we built before, but we're going to have to do biological sensors, chemical sensors, power source. Our current batteries are unlikely to fit inside red blood cells. It's a cool thing if you think about it. Some of you are looking horrified, but don't worry. Apple will still be making the red blood cell or something. So quantum systems are going to be everywhere. So what makes them powerful? One of the things is the wave-particle duality. And the other one, and for people who've seen me talk at BrisScience before, I apologise, you've seen me do this before, but it's the only way I know on how to describe entanglement, is I'm going to try and talk you through entanglement to show you why it's a weird thing. So Schrödinger coined the term in 1935. Actually, his grandson was raised in Queensland and studied quantum physics at UQ some time ago. And entanglement is correlations between things that defy common sense. If you had entangled playing cards and you're at the local casino, you'd get your hands broken because you would always win and they couldn't find out how. And okay, that was an analogy and a bad one. Schrödinger came up with an analogy involving radioactive decay, a cat, and violence. You know, hammers, poison gas, death. And I think the violence made it really attractive. By the way, it's carved into the building in the Great Court, so it's very famous. If you do a search for Schrödinger's cat on Google's image, you get a truly disturbing number of things, including Schrödinger's cat suit. I wonder what the probability is of me getting arrested in this. I would guess fairly high. Despite all of that, the analogy is not a terrific one because even physicists misunderstand what it's trying to say. But early on, someone who really understood what it meant was Einstein. And he and 2 colleagues, this is one of them, I think that's Rosen, in 1935 published a paper that said, reading Schrödinger's paper on entanglement made us realise that quantum mechanics can't be a complete picture of the world. So while we have shown quantum mechanics does not provide a complete description of physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. Isn't that nice that there's a possibility that we can describe nature? That's very nice. They published that paper. Bohr published a paper immediately after it that went, I don't know what it went. It's an unreadable paper. I read it first when I was 19. I hated it then. I hate it still. And I was very thrilled to find a few years ago that this very famous physicist, John Bell, a Northern Irishman working at CERN, hated the paper as well. I felt that Einstein's intellectual superiority over Bohr in this instance was enormous. a vast gulf between the man who saw what was needed clearly and the obscurantist. And what Bell discovered was a way of doing an experimental test. And he discovered that if Einstein was right, and maybe quantum mechanics means we just need to kind of drill down and get to a finer grain detail of nature, and we can't see fine enough. And these are called local hidden variables. And Bell said if Einstein is right and there are these local hidden variables, then something is happening faster than light and Einstein is wrong, because Einstein said nothing can happen faster than light. Or if Einstein is right and nothing can happen faster than the speed of light, then Einstein is wrong and there are no local hidden variables. It's win-win for Einstein. The idea that you could test this was electrifying. And a lot of the early advances in quantum technologies in the 70s and 80s were people trying to do exactly this, trying to build the technology with photons to test this and see what was going on. Here's an analogy. So I've got a conveyor belt to the left and a conveyor belt to the right. And on the conveyor belt, there are ovens. And the ovens are cooking cakes as they trundle slowly to the left and as they trundle slowly to the right. And because this is Quantum Cakes Incorporated, I'd like to make some money. I'm going to have quality inspectors. But unfortunately, my quality inspectors are Lucy on the left and Ricky on the right. And again, for those of you who know over a certain age, that's not a good sign. Lucy's going to measure the left conveyor, Ricky's going to measure the right, and they're not going to measure very often, but when they do, they're both going to measure at the same time. And they both have a coin, and they're going to flip a coin. And if they flip heads, they can randomly choose to measure, say, head for halfway. They'll open up the oven and just check, is the cake risen or flat? Now, it's destructive measurement. Once you've opened the oven, you've ruined the cake. But that's all right. They're not going to do it very often. Or, at the end, they're going to open up the oven and taste it and see if it tastes good or bad. And again, once you've taken a chunk out of it, you can't sell the cake. It's destructive, but that's all right. You're not going to do it very often. So your options are risen, flat, or good, bad. Everyone following so far? Grunt if you are. Great. Love to hear an awake room. Okay, so remember they're flipping heads and tails. So some of the times they're both going to measure heads. So that's halfway. They're going to test the state of the cake and see whether it's risen or flat. Quarter of the time. Quarter of the time, they're both going to hit tails, and they're going to taste tails for taste and see whether it's tasting good or bad. And the other half of the time, one will be halfway, the other one will be tasting, or that one will be halfway and that one will be tasting. Everyone following so far? Great. Now, the first thing they find is that when that quarter of the time that they're both flicking heads, they find 10% of that time that they open them up, both cakes have risen. Okay. It's neither good nor bad, it's just kind of a slow oven. But they also notice that whenever Lucy's cake has risen, Ricky's cake tastes good. Or whenever Ricky's cake is risen, Lucy's cake tastes good. Good so far? I promise I'm not trying to trick you. Everyone's looking at me deeply suspiciously, like I'm selling magic water or something. No, honestly, it's just straight logic. We good? Okay. So how often do Lucy and Ricky find that both cakes taste good? Now, if you're undergraduates, I'd make you think about it, but I'm going to take pity and let's walk you through it. They measure taste at both ends 25% of the time, and when they do that, 10% of that 25% of the time, they find both cakes taste good. 10%, so 2.5%. So at least 2.5% of the time, you'd expect both cakes to taste good. Okay, this is not a very successful business, but putting that to one side, does that seem reasonable to people? Hands up if you feel quite confident. Somewhat confident. Wishing you were watching the ABC. Okay. I admire your honesty, if not your taste. Okay. If you followed that argument, and I apologise if I went too fast, you're an extremely good company. That is Einstein's hidden variable argument. That is exactly Einstein's argument on what should be happening in any reasonable system. But the weird bit is, quantum mechanics says if the cakes are entangled, both cakes will never taste good. Despite the case that whenever this one's risen, that's good. Whenever that one's risen, this is good. And some of the time, both of them are risen. That's non-zero, but both cakes will never taste good. And that's just wrong. And that's just affronting, and that's why Einstein thought quantum mechanics was not a complete description of nature. The way to test that, this argument is exactly an argument that Bell did in 1964. We can't do this with cakes. We don't know yet how to entangle cakes. But we can entangle particles of light, photons. So about 20 years ago, or 18 years ago, some colleagues and I did exactly that experiment where instead of risen or flat, we now used whether the light was oscillating, the electric field of the light was oscillating at one angle or another angle. And instead of good or bad, if it was oscillating horizontally, we said that was good. If it was oscillating vertically, it was bad. The argument's the same. And we found that both cakes never tasted good. Well, experiments can make mistakes. How sure were we? Well, with two physical assumptions, and I'll get back to that in a minute, the probability of error was 0.323306%. I never want to do an error calculation like that again. You think you can just put it into a computer? Nah, it turns out computers just choke after about 50 zeros. So I actually had to think, a dreadful thing. What that means is, now the physical assumptions was something called the detection loophole. Did you detect enough photons or could nature be tricking you? And the timing loophole, are you sure that you were detecting things because before someone could send a signal at the speed of light? And they were shut this year by, now as of last week, 3 experiments around the world. So it really looks like that if there is a hidden variable theory that describes the world like Einstein said, then it requires things to go faster than the speed of light. Or if you're not allowing things to go faster than the speed of light, there's no local hidden variable theory. So, how are we going for time? 10 minutes? All right. So let me finish on an up. That's just, ugh. What are you meant to do with that? You can't do anything with that. And actually, that's where the field sat for about 4 decades. It was fun. It was the kind of thing that you did experiments in. But you would tell students, whatever you do, don't do that as your main thing for your PhD because you won't get a job. Okay? And in fact, one of the first people who did this experiment was a guy called John Clauser, and he lost his job at Berkeley and ended up sailing boats, famously. So it was really a non-trivial warning. Fortunately, the modern generation are more forgiving. What we can do with this kind of behaviour is something called quantum information science. What is information? Well, we're all used to the idea of I can encode information as binary digits, 0, 1, pointing up, 0, pointing down, 1. And if I have 3 bits, 0, 0, 0, or 0, 1, 0, or 1, 1, 1, I can store any one number between 0 and 7. And in general, I can store one n-bit number. But now I can have quantum bits. I can have these photons or neutrons or any kind of quantum system. And they can point up, 0. They can point down, 0 plus 1. Down. Or they can point sideways, 0 plus 1. Or they can point out towards you, 0 plus I1. For people who aren't used to I, it's just the square root of -1. Just think of it as another direction. In this case, that way. And now I can take a 3-qubit register and simultaneously store 8 numbers at the same time. Or I can take an n-qubit register and simultaneously store all 2 to the n numbers. Is that useful? Well, not if you can't do anything with it. So the other thing you need to do with information is operate on it with gates. This is a NAND gate. If I have 2 logical zeros, I get a 1. If I have a 0 and a 1, I get a 1. 1 and 0, 1. 1 and a 1, I get a 0. It's irreversible. If I get a 1 at the output, I don't know which of those 3 inputs it was. And for your phone, that doesn't matter. But it turns out that uncertainty has a thermodynamic cost, and it costs energy. So if you're wanting to build really efficient computers, then you want gates like this thing called the Toffoli, which is reversible. It turns out you could build any computer just of Toffoli gates, but no one does because it's too expensive. And we don't really need to worry about it. But for quantum computers, you will need a reversible gate. So this is something called the controlled NOT gate. It's like an exclusive OR. The weird thing is every output here maps uniquely onto an input. So if I get a 1, 0, I know I had a 1, 1. If I had a 0, 0, I know I had a 0, 0 coming in. And now, if I had the control being a 0 plus 1, if the qubit's pointing sideways and the target is, say, pointing up, then the output is either a pair of qubits pointing up or a pair of qubits pointing down. And I don't have information ahead of time which it is. And that's entanglement. That's that weird quantum cakes thing. And with that and the qubits, a 300-qubit register can store more information than the number of the atoms in the universe. And that's quite an impressive thing because the universe has got a lot bigger over the last 10 years. Is that useful? People have found useful things. 2 useful problems. One is called factoring, and one is called scaling, simulation. There are people called computer scientists. Amusingly, they don't know how to program. But they do know how to think about logical structures mathematically. And they divide the world. They're really interesting people. An extroverted computer scientist is looking at your shoes, introverted at theirs. Sorry, it's an old accountant joke, but it's very true, the computer scientists. They divide the world into soluble and insoluble problems, and they further subdivide the soluble problems into easy problems, ones that you can calculate quickly, and hard problems. You might remember the travelling salesman problem from school, or factoring. Factoring is, if I give you 2 prime numbers, 3 and 5, and ask you what's the multiple, that's easy. Yep, question? No? You had an arm up? No, sorry. Okay. Someone's just yawning. Sorry. Now we're both embarrassed. But if I give you a composite number, say 341, and I say, what are the prime factors of that? That's harder. Take a couple of minutes. If I gave you 1,000 or 2,000 digit composite number and said, what are the prime factors of that? We would still be here 10 years from now trying to figure that out. Now, that's the basis of modern internet security, but there is an algorithm in quantum computers called Shor's algorithm that can solve that efficiently. So to a computer scientist, watch the blue circle carefully, this is what a quantum computer does. It makes some hard problems easy. It doesn't solve all hard problems, it doesn't solve the insoluble problems. But because one of those problems is the basis of encryption, right now in the US, they're moving to a new encryption code that is quantum computer proof, because the US government doesn't want people 10 years from now to be able to read their emails from today. The fact that Shor's factoring algorithm exists, and I'll finish up on this, I think, means one of 3 things must be true. The first one is that something called the Church-Turing Thesis, which is the foundation of all computer science, is wrong. This is Church, and this famously is Turing. And the thesis is, all computational problems that are efficiently solvable by realistic physical devices are efficiently solvable by a probabilistic Turing machine. I've got to admit, I'm not worried if that statement's wrong. It doesn't mean much to me. But it plays the same role in computer scientists. Michael Nielsen, another local boy, pointed out here in 2004, it plays the same role in computer scientists that Galileo and Newton's work played in physics. It made it all computable. It made it all rigorous. If you talk to a computer scientist my age or older, they do not think the Church-Turing thesis is wrong. And they might be right. Maybe the problem is that quantum mechanics is wrong. Maybe it's this realistic physical devices. Maybe when we build a very big quantum computer, we'll find that it's impossible for some fundamental reason. Now that sounds like a nonsense, but Paul Davies, who used to be here at the University of Adelaide, published a paper saying that he believes a 399-qubit quantum computer will work, but a 400-qubit quantum computer will not work because the amount of information it contains exceeds the amount of information that you can store on the surface of a black hole. I don't understand that at all. It seems complete nonsense. But as an experimentalist, A, I don't have to, and B, I would love the idea that we've built a 399-qubit quantum computer, it's working, and we add one more qubit and it stops working and it's the universe's fault. How cool would that be? It's not my fault. That would be awesome. A third possibility is that a fast classical factoring algorithm exists, that we could just do this with normal maths and we've not been clever enough. Now that seems unlikely, but some very famous people think that's true. Peter Sarnak, a very famous mathematician at Princeton, editor of Acta Mathematica, one of the leading mathematical journals, said, I love Shor's algorithm because it proves to me that a fast classical factoring algorithm must exist. Or this year in Nature Chemistry, one of the leading quantum chemists, Gus Guzieria, said, I believe that there is an efficient answer to the strong correlation entanglement problem. Chemists, man. We just haven't found it yet. So maybe they're right. So, okay, interaction time. Which of these do you think is the case? Hands up if you think the extended Church-Turing thesis is wrong. Okay, 2 people. 3, quantum mechanics is wrong. Okay, I want to talk to you later. Fast factoring exists. 2 of the above, all of the above. Shh. A number went up at shh. Okay. So how do you experimentally test this trilemma? And the point is you can. So there's now a research program underway at University of Queensland, in Oxford, in Vienna, in Rome, where people are trying to test this and find out if one of those 3 things is wrong, which is a really exciting idea. A few years ago, it was just philosophy. And it's brilliant for an experimentalist because it doesn't matter what you do, computer scientists or theorists or mathematicians and chemists will be badly upset. So that's lovely. Is that the only reason to do quantum technologies? No. Another reason is something called the Church-Turing-Deutsch principle. You can save Church-Turing by just adding the word Deutsch at the end, which is that any physical process can be efficiently simulated on a quantum computer. So here's an example. This is an energy diagram. Red is low energy, blue is high energy, and I've got some carbon surrounded by some oxygen. And I want to know, does the carbon form with one oxygen to form carbon monoxide, which would be bad, or does it tunnel through and form carbon dioxide, which is better than carbon monoxide? And this is a problem that manufacturers worry about in catalysts and converters. Okay, not Volkswagen, but many people worry about. Apologies for anyone who drives a VW. Calculating these surfaces is hard. But it's 90% of modern physical chemistry. And once you've got that surface, you've got everything. You've got reaction rates and saddle points and everything you need to design a technology. Since the 1960s, people have come up with this amazing tree of approximate methods. And there's a branch over here called B3LYP. And the people who do that don't really speak to the people over here who do, what's my favorite, CCSD, open brackets, T, close brackets. They go to different conferences. They publish in different journals, but it works. For a large number of systems, it works. But we are now hitting problems where it doesn't work. Things like superconducting. It'd be lovely to have a room temperature superconductor. Why don't we? I don't know. Theorists, get going. The problem is the very base of this tree, the first step is get rid of entanglement because it's hard. But there are a number of systems now where we think entanglement is playing a physical role. So what we'd like to do is build quantum simulators where we can replace that whole tree with little specialist computers that can solve the hard problems efficiently and design the technologies for the next 10 years. We built a little quantum simulator with 2 photonic qubits. It ran up to 20 bits and it agreed with a calculation on this laptop, actually physically this laptop, done on 50 bits in MATLAB, to 1 part in a million. So even these little toy systems are starting to become quite powerful. Okay, finally, the other interesting reason to build quantum technologies is they're interesting physical systems in their own right. You type into Google search quantum computer and the first 4 things that came up are neutral atoms, ion traps, trapped ions, photons, neutral atoms, superconductors. And when I was a student 25 years ago, we didn't have a common language for these different branches of physics. They were literally different branches. We published in different journals. We didn't talk to one another. And today we do. We have this common language of quantum information. We're making connections. We're building hybrid systems, and things are going incredibly fast. It's really exciting. And if you had asked me even 10 years ago, would I expect to see any of this in The Economist, I would have thought you were mad. But here's an article, Quantum Computing Race, from earlier this year. This is superconductors, it's got ice on it. Photons, it's blowing up, seems appropriate. Calcium ions, it's got a magnet. On a little bit better, on the current race to build quantum computers and other quantum technologies. I think I'm going to finish there. Let me just show one last thing. The other thing, I keep talking about language barriers, and they're very real. A chemist, go back to your little beakers and tubes, sweetie. This is a physics conference. Earlier, what do you study? 1 atom. How about you? 2. Yeah, I wish that was more of a joke than it actually is. And sometimes 3. Biologist. Okay, so we are trying to break the barriers. We've got this new language, which are quantum technologies, these new toys and tools. A huge part of that is light, both as elements of themselves and as important connecting elements between other technologies. So with that, I'd like to thank you for your attention. and ask if you have, let's see if I can get this up, any questions. Take-home messages. Light is an amazing tool. Advances are happening everywhere, including right here in Brisbane, and the future's looking bright. Thank you.
Fantastic stuff, Andrew. Yes.
Okay. Meanwhile, Helena just gave me this card where we can make all kinds of diffraction patterns. And I've just managed to shine one into my eye.
While Andrew's playing, if you have a question, feel free to wave it around, and Jackie and Anko will come round and collect that.
Oh, cool. Oh, that one's really nice. Okay. Yeah. You can come play with this later, but you must keep one eye shut so you retain vision in one eye. You think I'm joking?
So we're going to take questions just a moment. Feel free to grab a drink if you want for a moment. Just a couple bits of housekeeping. First of all, thank you all, of course, coming along tonight. This was both a UQ alumni event and a BrisScience event, so we thank very much UQ for their continued support of BrisScience. Our talk next month will be on the Monday the 9th of November, and we're going to be talking about Google Maps. And we've got a fantastic panel of town planners and geographers and geologists talking about how Google Maps has changed the way that we do research and manage the world. So it'll be a great talk, and we look forward to seeing you all along for that one next month. All right, are you ready for some questions?
I am. By the way, the Come Join Us is a genuine invitation. One of my PhD students is 10 years older than me. We will take anyone who wants to come. Just get your science degree first.
All right, Andrew. First question for the night. If light phases cancel each other out, what happens to the light energy?
Ah, that's a good question. It goes somewhere else. So, no.
Okay,
Literally. No, let me show you. That's an excellent question. And I didn't mean to make that as flippant as it sounded. Sorry. My youngest had me up at 4 a.m. It's been a long day. What can I say? So, in this one here, where the light is... What do I do with the laser pointer? No. Sorry, Joel. No. Where the light is going 100% there, here it's cancelled. So 100% of the light goes in, 100% has to come out. So it all goes here and none of it goes there. But if I vary the phase between the arms, I can make it go half there and half there. Or if I put in a little extra thickness of glass, I can make it all go there and none of it there. Energy is conserved. Okay. So in the light beam, when I said that you're getting the patterns and you get the dark stripe in the middle, the energy that was initially in the round pattern goes further out. But it's still, overall, I've got all the energy.
Good. Okay. All right. Next question. This is from Chris. What do you see as the practical main application for quantum light theory in the near future?
Ooh, good question. I'm going to cheat and say the practical application so far has been things like solar cells and lasers. You cannot understand those and you cannot design better ones unless you have quantum theory of light. But it's a semi-classical theory. The light can kind of be a field and the matter can be quantized. So proper fully quantized light, my guess is going to be in any future quantum technology, whether it be superconducting circuits or ions or photons themselves, the elements hooking them up, you really need to understand quantum light to do that. And in the current server farms, like in Google, when you type a search into Google, don't do that. It costs energy, okay? There's a building about this size full of cards. The cards are all put together in a rack. The speed increases in the last 15 years have been because they blow cold air between the cards, and they used to have wire at the back. And when you had copper at the back, you couldn't blow very much air through them. So they replaced the thick bundles of wire with just single fibre optics, and you could blow more air through. So in the last 15 years, just light for that purpose, which you don't need a quantum theory, has led to huge speed improvements. But for quantum devices, you'll need the quantum theory of light. And there are people selling things at the moment, like quantum communication systems that are based on this quantum theory of light, but I don't think that'll be a very big market. Could be wrong.
All right, the question about probabilities. In computer science, the random function appears completely random, but if the system is reset with the same seed, the numbers come out the same way. Could the probabilities of quantum mechanics be similar?
That's a really good question. As far as we know, no. No one's seen a repeatability like that, and people have looked for it because we're desperately looking for some clues to understand what this bigger theory is. There's a Dilbert cartoon from a few years ago where they take him down to the demons in the accounting department. Here's our random number generator demon, and the demon's going 9, 9, 9, 9, 9. And Dilbert goes, that doesn't sound very random. And one of the other demons goes, that's the thing with random numbers, you just don't know. But we have looked and we've done tests. I can set up the same kind of experiment, just going back 2 slides. This experiment is one of the best random number generators. Ahead of time, I don't know if this photon's going to go that way or this way. I've got no predictive power. I can know overall 50% will go this way or 50% will go that way, but ahead of time for any given pulse, I can't know. And that's been tested to great precision out to billions of counts. So we haven't found any evidence, but we'd love to. It'd be cool.
We have a couple of questions that are now sort of moving a little bit further afield. A couple of questions touching on to faster than light. And I'll sort of paraphrase them together. Do you think that speed of light is indeed a hard limit, or do you think that we could discover something that travels faster than light?
Okay, I'm far from an expert on faster than light stuff, I should point out.
So humble.
No, but we have colleagues at UQ who are, right? This is their bread and butter. We have lots of good reasons to think that you can't send information faster than the speed of light. But that's not to say you can't have models of the world where you have things going backwards in time and forwards in time, and they add up to give you something that goes forwards at the speed of light. And that might be, by the way, one of the solutions to the local hidden variable theory. You can have a non-local hidden variable theory, and that means you've got things going forwards and backwards in time, but they all add up to give you things that are speed of light slower. If we could send things faster than the speed of light, all of quantum science would change, because at the moment when I have one of these qubits, I can't make a perfect copy of it. So normally with 3 bits in a row, 0, 0, 0, I can make a perfect copy of those, give them to you. I get hit by a truck, you've still got the information. But with quantum, I can't do that. And it's called the quantum no cloning theorem. And it turns out the only way around that is if I can send information faster than the speed of light, which no one was expecting. Who ordered that? So there's really deep connections. There is in general relativity apparently a possibility that you can send things faster than the speed of light. If you warp space-time, you can get a bubble that goes faster than the speed of light, but you need negative mass, and we don't know how to do that. I could do with some negative mass. At the beginning of the year, I determined to lose 10 kilos, and I'm happy to say 15 to go.
All right. 2 more questions. We have time for 2 more questions. This is from Murray, who asks if Mephistopheles, and I'm not sure about the exact pronunciation for that, I've only read it, but came to you like Faust and gave you the chance to know one thing about the quantum world that you don't know already, what would it be?
Ooh, one thing.
Just one, and that was highlighted in a big box, which was
one
bolded.
thing wouldn't be really useful. A whole bunch of things. I don't know. Let me think about it for a couple of minutes before we move on to the next one. Yeah, okay. I've got it. I would like to know if the wave function is a real thing or just a mathematical description of nature. And the reason why that's a thing at all in quantum mechanics is even in 1905, a lot of chemists thought that atoms were just a mathematical device and they weren't real. And Einstein's paper on Brownian motion showed that atoms were actually real things. They weren't just a handy calculational tool. And at the moment in quantum mechanics, this wave function that we use to describe everything, lots and lots of people in quantum mechanics think it's just a mathematical tool. Some people think it's real. We've just started doing tests. I'd really like to know, actually what I'd like to know is the experiment I could do to prove that one way or the other. That's my one thing I want to know.
Always with the eye on Nobel Prize, yeah.
Stuff the Nobel Prize, I just want, a week off.
All right. Well, we just have one final question, which I thought was very appropriate. I'm not sure how much you know, but on the 26th of October 1985, a DeLorean DMC-12 departed Hill Valley, California. Could we expect to see a blinding flash of light on 21st of October at 12:29 Universal Time?
So you're going to think this is a setup, but I'm really glad you asked that. Next Wednesday is that date. I'm at a conference in California. I'm the first talk of the morning. and it's the day that Marty goes in the future. So, and if I can get this to work, I'll be a happy boy, but I don't think I can. Come on. No, it's not going to work. So I got online last night and ordered a puffy orange jacket, which I'm going to wear through the talk. Because certain things must be done.
Well, we'll look forward to seeing you back to the future then.
Okay,
All right,
thank you.
could you give a huge round of applause for Andrew White for his talk this evening? We do have some refreshments outside, so please join us. Please harass Andrew. He loves to talk about this stuff and he'd be happy to talk more.
If anyone wants to come play with this stuff safely, please do come up, but I'll have to hang around because if I blind anyone, the paperwork.